This is the problem solving session for AC circuit situations involving capacitors, inductors, and transformers. And we'll walk through the problems that we looked at in class that line up with the chapter. Question number 1 says the figure shows the voltage and current graphs for a resistor. And this cues us in that this is an alternating current circuit because the current is going from a maximum positive to 0 to a maximum negative to 0 back to a maximum positive. The voltage is doing the same, and it asks us what is the value of the resistance R. Well, the resistance can be figured out using Ohm's law for an AC circuit just like it was for a DC circuit. And I can really pick the voltage and current at any time I want to do this calculation. Clearly I wouldn't want to pick when they're both 0, but the resistance is going to equal the potential difference divided by the current. And let's just pick the beginning. The maximum voltage, or the voltage at time 0, is 10 volts. The current at that time, I got to read it off the right hand side of the graph, is half an amp, and that means the resistance of this is 20 ohms. What is the EMF frequency F? Well, again, we see that this voltage and current are oscillating. The EMF, or the voltage, takes 0.04 seconds to go through one complete cycle. So the period of that is 0.04 seconds. Frequency is the inverse of the period. So 1 over 0.04 seconds gives us 25. The units are inverse seconds, but we more commonly write that as hertz. A hertz is a cycle per second. The next couple of problems looked at transformers. This one says a soldering iron uses an electric current in a wire to heat the tip. A transformer with 100 turns on the secondary coil provides 50 watts at an RMS voltage of 26 volts. Assume that the soldering iron is plugged into a 120 volt outlet. So it's probably not necessary, but I'm just going to sketch my soldering iron outline here and think about how this thing must be engineered in order to be producing what we're talking about here. So somewhere in this soldering iron is a transformer, which would have some sort of conducting core of steel or iron. And the wires from the input come and they coil around this side. That's known as the primary side. And then on the secondary side we have another coil, and that is connected somewhere in the tip to a resistor, which when it heats up is providing the heat on my soldering iron. So what things do we know here? Well, we know on the secondary coil the number of turns is 100. The power on the secondary side is 50 watts, and the voltage over here on the secondary side is 26 volts. Over here we're connected on the primary side to a 120 volt outlet, and that's it for the data that we know. Alright, what is the resistance of the wire in the iron? Well, we can do this back to our idea from the electric circuits unit that relates power to potential difference and current. But again, we showed that that could be also rewritten as the square of potential difference divided by the resistance. And that means the resistance is equal to the potential difference squared divided by the power. This is, I'm looking at my secondary side of this transformer, so 26 volts squared. The power here is 50 watts, and if we calculate that out, we find that the resistance is about 13.5 ohms. How many turns are in the primary coil? Well, there's a few ways that you can do this, but the number of turns in the primary coil, the ratio of that to the number of turns in the secondary coil, is the same as the ratio of the potential difference in the primary coil to that in the secondary coil. And we know both of these potential differences. So the number of turns in the primary coil is the voltage in the primary coil, 120 volts, over the voltage in the secondary coil, 26 volts, times the number of turns in the secondary side, which is 100. And if you punch that out, you get 462 in change. But when these are doing numbers of turns, we always round to the nearest integer value, since you can't really have 0.34 of a turn or whatever that number would happen to be. Finally, what is the current in the primary coil? There's again a couple of ways that you can approach this. The number of turns in the primary coil to the number of turns in the secondary coil, as again we said in part B, is the same ratio as the voltage, but it's actually the inverse of the ratio of the current. So it's the same ratio as the current in the secondary coil to the current in the primary coil. Or you can work with the assumption, that, which we do in this theoretical case, that there's no power loss. So power out equals power in, which tells you that the current on the secondary side times the voltage on the secondary side equals the current on the primary side times the voltage on the primary side. And either way you do that, the current in the primary coil is going to equal the power on the secondary side, which is this whole thing here, divided by the voltage on the primary side. So if we take 50 watts and divide by 120 volts, we get the current on our primary side to be about, well, it's exactly 5/12 of an amp, but for you that are not fans of fractions, that's about 0.42 amps. Problem 3. A power pack charging a cell phone battery has an output of 0.9 amps at 5.2 volts. They're both RMS voltages. What is the RMS current at 120 volt wall outlet when the power pack is plugged in? Again, habit of mine, probably not necessary. So I always sketch my little transformer symbol and put what I know. So the output, which would be the current on the secondary side, is 0.9 amps. The potential difference on the secondary side is 5.2 volts. The potential difference on the primary side is 120 volts, but we want to know how much current is coming in. And again, we can do this with the ratio of the number of turns argument, but it's probably simpler to say power in is going to equal power out, which, by the way, is not true. This is an approximation in an ideal physics world. If you've ever used a power adapter and you've ever felt it getting warm, that's because some of the energy that's in this system is being dissipated as heat. You never get out exactly what you put in here. But the current on the primary side is going to equal the current on the secondary side times the potential on the secondary side divided by the potential on the primary side. So that is 0.9 amps, 5.2 volts over 120 volts, and that comes out to a current of 0.039 amps or 39 milliamps. Problem 4 and 5 looked at capacitors. 0.23 microfarad capacitors connected across an AC generator that produces a peak voltage of 9.7 volts. We want to know the peak current if the frequency is 100 hertz, and what happens to the peak current of the capacitor if the frequency is 100 kilohertz. Well, the new idea introduced was that capacitors and inductors both have something known as reactance, which acts as resistance, but it changes obviously throughout the operation of the circuit. And for a capacitor, capacitive reactance is 1 over 2 pi f times the capacitance. There's also a form of Ohm's law which says the peak current in one of these circuits is equal to the peak potential difference, not divided by the resistance, but divided by the capacitive reactance. And if you put this in here, put both of these relationships together, you get the current is equal to the potential difference divided by 1 over 2 pi Fc, which you can simplify or at least get rid of the fraction piece of this and put everything up in the numerator. So if we go ahead and plug in what is known here, the peak current is going to be 2 pi. The frequency we'll start out with as being 100 hertz. The potential difference across this is 9.7 volts. The capacitance is 0.23 microfarads, so that's 0.23 times 10 to the negative 6 farads. And if we punch all that into a calculator, we get 1.4 times 10 to the negative 3. The units of current are amps, or if you prefer, we can write that as 1.4 milliamps. We shouldn't need to redo the calculation to do part B, since we showed here that the current is directly proportional to the frequency. If the frequency is instead 100 kilohertz, that's 1,000 times bigger than this, which means the current that we're going to produce is 1,000 times bigger than this, so that's just 1.4 amps. Problem 5, a 40 microfarad capacitor is connected across an AC generator that produces a peak voltage of 7 volts. The peak current is 0.5 amps. So what is the oscillation frequency? Well, again, we last problem, put together these two expressions to say that the current was 2 pi f times the potential difference times the capacitance. If we now solve this for frequency, frequency is going to equal the current divided by 2 pi times the potential difference times the capacitance. We're told peak current is half an amp. 2 pi is 2 pi. The potential difference is 7 volts. And the capacitance, 40 microfarads, or 40 times 10 to the minus 6 farads. And if I crank that into the calculator, I get a frequency of 284 cycles per second, or 284 hertz. The final two problems dealt with inductors in an RL circuit. Number 6 says a 15 millihenry inductor is connected across an AC generator that produces a peak voltage of 9 volts. What's the peak current through the inductor if the EMF frequency is 100 hertz? What is it if it's 100 kilohertz? So this parallels number 4 that we looked at. Well, just like a capacitor, an inductor has inductive reactance, and instead of being inversely proportional to the frequency, it is directly proportional to both the frequency and the inductance. And so again, if we think of reactance as being resistance to flow in the circuit, if I make a bigger inductor, a bigger coil, that's going to have more resistance to flow. Also, if I up the frequency, I'm changing the direction of the current more rapidly, meaning I'm changing the magnetic flux in the middle of that inductor more rapidly, and a bigger change in magnetic flux means a bigger back EMF, and again, more resistance to flow in that circuit. You can also write the form of Ohm's law, that the current through the inductor, the peak current rather in an inductor circuit is equal to the peak potential difference divided by the inductive reactance. And so if I plug in, I've got 9 volts divided by 2 pi. My frequency is 100 hertz. And my inductance is 15 millihenries, or 15 times 10 to the minus 3 henries. If I punch all that into my calculator, I get a current of 0.955 amps. B, again, I shouldn't have to do all the steps of the calculation. If I realize that current is inversely proportional to the frequency here, then making the frequency 1,000 times bigger is going to make the current 1,000 times smaller. So the current here is going to be 9.55 times 10 to the minus 4 amps, or 0.955 milliamps would be another way to say that. And the final question reads, a peak current through an inductor is 20 milliamps. What's the current if the EMF frequency is doubled? What's the current if the EMF peak voltage is doubled? What's the current if the frequency is halved and the EMF voltage is doubled at the same time? Well, as we showed just on the previous problem, the peak current is equal to the peak voltage divided by the inductive reactance, and that's the voltage divided by 2 pi times the frequency times the value of the inductor. So if I have 20 milliamps originally and I double the frequency, if I make the frequency twice as big, that makes the current half as big, and I will be at 10 milliamps. What's the current if the EMF peak voltage is doubled at the original frequency? So I go back to my original frequency, but I double the peak voltage. Just like you would expect from Ohm's law, if you double the voltage, you're going to double the current. So the peak current is now going to be 40 milliamps. What if you do both of those things at the same time? What if you have the not doubling the frequency. What if you have the frequency? So I cut this one in half. That has the effect of doubling the current. And at the same time, you double the EMF. So I'm having this, which doubles the current. I'm doubling this, which also doubles the current. Both of those together is going to quadruple the current. And I end up with 80 milliamps of current in that situation. So those were the problems we looked at dealing with capacitors, inductors, and transformers related to the AC electricity chapter in the textbook. As always, if you notice any error in these solutions or have further questions, I hope you reach out and ask me about it. Thanks.